In this video, we'll discuss polynomial functions and their graphs. Now, there's some key polynomial functions you should recognize. You should be able to recognize a linear function, a parabola or quadratic function. You should be able to recognize a cubic function, a quartic function, which looks very similar to the parabola, but if you notice that where your minimum or maximum is, it's a little bit wider than just reaching to that specific point. The square root function, and then the absolute value. And the absolute value makes that v for the absolute value. And that's because no matter what number you input, you always get a positive output. Now, when we look at the third and fourth degrees, they can actually change a little bit in how they look when we graph them. For example, we could have the reflection across the x-axis when the x cubed is negative, but you can also, depending on where the zeros are, get more pronounced relative minimum and maximum values, which give it this kind of, like it has two humps, almost like a sideways S. So the values can change. So in general, this is what you could look for if it is third degree. With the fourth degree, again, you get that kind of U shape because it's an even index and it widens a little bit more than, say, a parabola does. But again, you can get actually relative minimum and maximum values that make it look somewhat like a W or an M depending on where the zeros are for this function. So you may not always have a calculator with you, but if you see a graph, you should be able to recognize, does this look like a parabola in a quadratic, a third degree, or a fourth degree? Those should be able to come to you relatively quickly. Now, with any of these functions, we should be able to recognize the shifts that occur within the function. So we know that graphically that y equals f of x minus h plus k means that the graph is going to shift h units horizontally and k units vertically. And again, it's got to be x minus h for that shift. And this is all in relationship to that original parent function, like y equals x, or y equals x squared, or y equals x cubed. That's where the shift is occurring. So if I had f of x equals the quantity x minus 4 to the fourth plus 1, I'd want to say, okay, how's that shifting? Well, I am shifting positive 4 units to the right and positive 1 unit up. So if I think about my parent function being x to the fourth, that means I'm going to go to the right 4 and up 1, and I'm going to put the exact same graph. That's the difference. It's just shifting the graph. Nothing else changes about it. It's just shifting to a new location. So if I graphed only the quantity x minus 4 to the fourth plus 1, it would look like this. Now it can also be handling rational functions. In a rational function, we say that y equals f of x over g of x, where they are both polynomials. The key here is that this is only valid when g of x does not equal 0. So that means that you can have asymptotes. And the graphs of these can vary quite a bit. For example, here's 3 different rational functions that I graphed, and you can see how some have asymptotes, and this one on the right has no asymptote, even though it's got this interesting hump in it. Now, it will have points on it that are undefined likely based on the denominator if there is some specific point where both the numerator and denominator equal 0. So when we're looking at rational functions, we're often asked to find the asymptotes, both the horizontal and the vertical asymptotes. Now, the vertical asymptote is one that you've most commonly seen, which is I want to look for a value of x that when it is substituted into the g of x, it makes it 0, while the f of x function does not equal 0 at that specific point. If it does, what's going to happen there is that that point is going to create a hole in my graph. And that's really hard to see. You almost have to go over the graph to see it, and it'll say that's undefined at that value. The other one is the horizontal asymptote. And to understand the horizontal asymptote, here I have taken my expression and worked it out as to what would this function really look like. It would look like a sub n, some number, x to the nth, all the way down to x to the first plus a constant divided by x to some other exponent all the way down to x to the first plus some constant. Now, to tell the horizontal asymptote, it's the leading coefficient. I need my highest degree in the front. That's the one I'm looking for. Where's my highest degree? And if things aren't expanded fully, I need to expand the expression so that I understand where's my highest degree. If my highest degrees are equal, say like this is 2 and this is 2, then I look at their coefficients, and that will tell me where the horizontal asymptote is. And it's the numerator's coefficient divided by the denominator's coefficient. If my denominator's degree is higher, then the horizontal asymptote is at y equals 0. If the numerator's degree is higher, there is no horizontal asymptote. So it's possible that it can be 0, some other real number, or that there is no asymptote for a horizontal asymptote. So let's look at some examples to help us with this. Say I have y equals 4x plus 1 over the quantity 2x minus 6. So let's start with the vertical asymptote. I'm going to see when does 2x minus 6 equal 0. Well, I add 6 to both sides. That gives me 2x equals 6. Divide by 2, I find that x equals 3 is when I would have a vertical asymptote. But I do want to verify that it's true by looking at my numerator's expression as well. So I'm going to substitute 3 in. 4 times 3 plus 1. And I want to know, does that equal 0? I hope not. If it does, so 4 times 3 plus 1 gives me 12 plus 1, which is 13. 13 does not equal 0. Therefore, this is a vertical asymptote. Now let's look at the horizontal asymptote. For here, I'm looking at my leading coefficients and my variables here. They both are a first degree. So they have the same degree. So what I'm looking at then is that the horizontal asymptote is going to occur at the fraction of those two coefficients. So y equals a over b. My a value is 4. My b value is 2. So that's 4 halves, which is 2. And if I was to graph this, I would see that I get what looks like a hyperbola, and I'll have a vertical asymptote at 3 and a horizontal asymptote at y equals 2. Now let's look at one other example. Say I've got x squared minus 16 and x cubed plus 27. Start the vertical asymptote. That's the x cubed plus 27. So when I do this, I'm going to subtract 27 from both sides and take the cube root. And that will give me that x is negative 3. I do want to verify that this is true, so I substitute into the other expression and verify that it does not equal 0. So negative 3 squared is positive 9. 9 minus 16 is negative 7. And negative 7 doesn't equal 0, so there is an asymptote at x equals negative 3. Now, the horizontal asymptote then, I'm looking at my two leading variables. My highest degree is in my denominator. That means that the horizontal asymptote occurs at 0. So that means I have a vertical asymptote at x equals negative 3, a horizontal asymptote at y equals 0. And if I were to graph them and try to zoom in, I would see there's my vertical asymptote at negative 3. Here's my horizontal asymptote. And this looks kind of weird, but if you zoom out, you can see that it goes closer and closer to 0 as the graph goes towards negative infinity and positive infinity.